Hey everybody, welcome back. This is Math 21 at College of the Sequoias, Introduction to Statistics. And today I'm working on Chapter 7. It's a fairly short chapter, but Chapter 7 is on the normal and standard normal distributions. And we'll start off with the normal one, and then that's 7.1. And in 7.2, we'll look at the standard normal distributions. So, the normal distribution, 7.1. In both of these, we will use stats calculators normal. All right. But for now, let's just talk about the normal distribution. The normal distribution is symmetric and bell-shaped. And this will be our most important distribution from here on forward. As you'll see when we get to chapter 8, we can make everything look approximately normal, and that's desirable. So, looks like a bell. It's centered about the mean. And we can go one deviation in either direction. This should look familiar. It should look like the empirical formula or empirical rule. And at one deviation away, the graph goes from decreasing. The line is decreasing as it moves. And it gets to this point and it starts increasing. It doesn't, the steepness of the line is slowly getting more and more upwards or flattening out. And it happens on both sides. If I had drawn this a little bit better, they would be equal right there. These are called inflection points. Just for some, here's your useless, well, not useless, your Jeopardy knowledge. And you'll notice, hopefully you notice, that a normal distribution looks a lot like a relative frequency. Looks like relative frequency with bell-shaped data. When there's a lot of bell-shaped data, or when there's a lot of data that makes a bell shape. All right. And that's what makes it normal. Normal is this bell shape. And they're also symmetric. And what symmetric means symmetric is based off the word symmetry. And symmetric means if we draw a line down the middle, the two halves look like reflections of each other in a mirror. All right. And the normal distribution has several properties. So let's talk about the properties of the normal distribution. And this holds true for the standard normal distribution of 7.2. But the standard normal distribution has a little bit more going on. The first property is the area underneath the curve or beneath the curve equals 1. And thus lines up with with proportion or probability models. Okay. We did mention it's symmetric. And the line where we draw it down the middle, it's symmetric about the mean, mu. For the normal distribution, since it's bell-shaped, the mean is also the same thing as the median and the mode. Should be the most common entry. But we frequently use the mean. So the peak of the hill is when x equals mu. As we go from left to right, x increases like a number line. A little bit more information. The final thing that happens is the graph never touches the horizontal axis. Graph must never touch the horizontal axis, and it doesn't. Which means when I'm going to redraw that on the next screen and illustrate it. If we've got our graph like this, the horizontal axis is the flat line at the bottom, and we've got our bell-shaped distribution. There's our mean. These two lines never touch. It might get so close to it you can't see it with the naked eye. Same thing over here. They don't touch. That and the axis don't touch. You may not be able to see it with your eye, but if you magnify it in close enough, they're not actually touching. All right? This can lead, since the area under the curve can lead to, it has to equal 1, we might have something like this where, let's say, whatever the mean is, let's say the standard deviation is 1 and it's taller for this graph. But if the standard deviation gets bigger, it might get flatter in the middle, but it's taller at the ends. That might be something like sigma equals 2. So if the center gets shorter, there's less near the mean, then there's got to be more on the edges. The symmetry is saying that direction has 50%, that direction has 50% of the graph, and they look like reflections. This matches up well with our empirical rule. So I'll bring it up again. Let's do the empirical rule. And I'll just label them here. Mu plus sigma, mu plus 2 sigma, mu plus 3 sigma, and we go the other way, we subtract sigmas. Minus 1 sigma, minus 2 sigmas, minus 3 sigmas. So I'm writing them there. To make it easier to illustrate down below, I'm just going to write the sigma values. So we got mu in the middle, sigma, or plus sigma, plus 2 sigma, plus 3 sigma. Makes it a little bit clearer to see. The empirical rule follows that normal distribution. So 50% is to the left. 50% of the area is to the right. Between the first two deviations, going one in either direction, we've got 34% and 34%, which makes a net value there of 68%. The next region has 13.5% in each region. That ink's still wet and it's smudged. And so between these two, this is 95%. And this is our usual zone. We categorize it as data as being in a usual area or expected area, or unusual zones are outside of it. If data is unusual, it's not like the mean at all. It's far away from it, and we call it unusual. It's the outer part, where this region here is 2.35% between 2 and 3 deviations, and finally 0.15%. Okay, which effectively puts 2.5% on either side in the unusual zone, making it 5% is unusual. We've talked about that before. Something being unusual happens less than 5% of the time, and that's how we're indicating it. It's in the outer 5%. If we look at 3 deviations, going from -3 sigma to +3 sigma, this is 99.7% of the data of the area. And hopefully you will have this table memorized by the time you get to the midterm. You will need this. I've drawn this at least 4 times, and problems have been given to you that have it in it. And there's a couple ways at looking at this area under the curve. So let me give you descriptions of it. I told you it lines up well with probability. I even said the word proportion. And the reason why is that it lines up well, depending on how I use the word, it lines up well with it. For a given area under the curve between 2 values. we can say this represents, it can be written two ways. A, the proportion of the population that possesses a specific trait or characteristic it's really whatever the curve is about. Like if it's an IQ curve, it doesn't tell us anything about the weight, it tells us about the intelligence. So it's the proportion of the population that possesses a specific trait or characteristic, the one in question. Or B, if an individual is randomly selected from the population, the area represents the probability that they possess the trait. So area is associated with proportion or probability. And when it follows a normal distribution, the homework usually tells you that the data is normally distributed. Okay. Let me spell out this with the IQ test. Let me put the IQ test information up here and give you an example of what I mean by A and B. So the standard IQ test has a mean of 100 and a standard deviation of 15. And we'll just throw in the percentages. I'm writing them there, right there. And let's say we're looking at 85 to 130. The range 85 to 130 has 34. 34 is 68 and 13.5. If we add those up, we get 81.5%. Or 0.815. So what it means is, we can interpret this two ways. 0.815 or 81.5% of the population has a score between 85 and 130. Or B, the probability of a randomly selected person having a score between 81 or between 85 and 130 is 0.815 or 81.5%. Okay. So section 7.1 is going to have you working with these graphs a lot. When I want to look at this in StatCrunch, stats, calculators, normal. Do this on the next page. And we'll look at the IQ test for now. So mean is 100, standard deviation is 15. Stats, calculator is normal. We need to enter the mean and the standard deviation. And I just got done saying between 85 and 130. If we click on between, and I say between 85 and 130, it's going to be close to the value I gave you, the 81.5%. 0.8185. So the empirical rule doesn't match exactly. One deviation outward should be 85 to 115. It should be 68. And it's close. Memorizing 34% on each side is a lot easier than remembering 34.1345%. So the empirical rule rounds it really. You'll notice also in the normal calculator, if you put in the mean and standard deviation, you can tell it. See up here, it says 68, 95, 99.7 ticks. I can click on it and it's showing me the values that I put right here on my graph. I added 15, 30, and 45 increments of 15 or subtracted increments of 15. So the 68, 95, 99.7 is following the empirical rule. And it shows it there. If you turn it off, it just shows, it doesn't show it adjusted to the mean. Having it is a good thing. It shows you the deviation. So if you click it on, it shows you the deviation. We have some options. We can look at different things. So I said we did the 85 to 130. What's the probability that a person has an IQ score below 86? Below 86 would be like that. Do I have that option? No, I don't. I can't do less than or equal or less than. On the normal, on these continuous distributions, less than is the same value as less than or equal to, just like greater than or greater than and greater than or equal to. The reason why on a continuous distribution, the probability that x equals a specific value is 0. It's like a rectangle with no width, like a very narrow rectangle, no width. Of 0 width. The only time we have width to it is if we give it more than just a single pinpoint line where we can make a box. So, probability that x is less than or equal to 86. (0.1758) or 7153. So we can do things like that. That's what the normal calculator will give us, and it saves us a lot of work, and it's telling us either the proportion of people that are in that category. So 17.5% of people have an IQ score below 86. Or it's the probability of selecting a person at random, the probability that they have a score lower than 86. Again, we can, I recommend giving this a try on your own. Remember, we're going to, I'll start it over. Stats, calculator is normal. Why don't you guys give a try to the probability that x is greater than or equal to, what's a good score? What's considered intelligence or genius IQ? Let's look that up. What is the lowest score on the IQ test for a genius? What do we call a genius? A score of over 140 is considered a genius or near genius. So let's look at what's the probability of a person being a genius. I imagine this article tells us, but let's go back and look at it ourselves. We need to change the mean to be 100, the standard deviation to be 15. We're going to say x is greater than or equal to 140, and we click compute. 0.00383038, or in terms of percentages, we move it right twice. 0.383% of the population is a genius. Falls in the genius range. That's considered the score for genius. As sad as it makes me, mine is not 140. It's below it. But I'm still smart. Let's look at some other examples. Can be unusual. The weight of giraffes is normally distributed. With a mean weight of 2,200 pounds. (2,200) is another way of saying 2,200. And a standard deviation of 200 pounds. They're heavy. And our job, we are going to draw a normal distribution. With the 68, 95, 99.7 ticks. And B, shade the area left. X equals 2,100 pounds. And what is this telling us? Okay. That's our problem. So we're going to start off. Well, first you need to identify the mean and the standard deviation. They give us the mean is 2,200. Standard deviation, they tell us, is 200. So we put 2,200 in the middle. We add increments of 200 going to the right. We'll do it 3 times. And we'll subtract 200 going to the left 3 times. $2,100 is right here. So we're the shade in the area under the curve to the left is that region right there. What does that mean? What does that tell us? Well, let's put in that in StatCrunch. 2,200 and a deviation of 200. And where we're looking for less than or equal to 2,100. And we get probability that X is less than or equal to 2,100 is 0.3085374, which is about 0.309. Or let's go to 4 decimal places, 3085. And we have 2 ways of interpreting that. If I write it as percentages, 30.85% of giraffes. What does this mean? What are the numbers over here to the left of 2,100? I've got 2,000, 1,800, 1,600. These are all weights. And we're saying, so we must be talking about giraffes in this range. 30.85% of giraffes weigh less than 2,100 pounds. And the other interpretation we have is a randomly selected giraffe. Has a 30.85% chance of weighing less than 2,100 pounds. Okay. Now, this is just giraffes. We talked about, I'm pretty sure we talked about the Z-score before. To compare different, this might have just been with a student that asked me. To compare different scales though, take a look at that. On that piece of paper. look at that in a second. To compare different scales, we can convert scores to z-scores. Any score to a z-score. And the formula for it, it's based on z is the number of standard deviations away from the mean. For a specific x value. Which means x equals the mean plus z times sigma. It's our multiplier on our standard deviations. If we solve for z, we get z equals x minus mu over sigma. Okay? The z-score, in z-score form, the z-score distribution is normal. All we've done is change the scaling on the bottom, is normal with a mean of 0 and deviation of 1. Okay, this allows us to compare different categories. Maybe if we had male giraffes versus female giraffes, or if we wanted to compare one giraffe relative to his kind versus an elephant relative to his kind, they weigh different amounts. Which one's larger compared to his species? We could use z-scores. The z-score, when it has a mean of 0, a deviation of 1, and it's normal, these two criteria make up the standard normal distribution we're going to look at in 7.7 or 7.2. Okay? So let's find the z-score of our 2,100-pound giraffe. The 2,100-pound giraffe has a z-score of, well, z equals 2,100, that's the giraffe's weight, minus the mean weight, which was 2,200, over 200 pounds, which was the standard deviation. This is negative 100 over 200, or negative 0.5 when you calculate it. Negative 0.5 or negative 1/2. Why don't you guys try, what's the z-score for, what if the giraffe weighs, he weighs 2,500 pounds. Calculate that out real quick. $2,500 minus 2,200 over 200 is 300 over 200 is 1.5. Okay. Where is that on our graph here? I could put 2,500 here. Most giraffes weigh less than 2,500 pounds. We can see that. If we wanted to say between 2,100 and 2,500 pounds, we get that. And I'm going to show you how the z-score compares to this. So let's just draw what I have on the screen. Giraffes between 2,100 and 2,500 pounds. Assuming that I have the correct mean and standard deviation. I don't know, I'm not a zoologist. I picked those numbers. On the graph, if we shade it, we've got 2,200, we got 2,000, we've got 2,400, we've got 2,600, 2,100 to 2,500 is this region right here. And StatCrunch is telling us the probability of that is 0.62465526. The z-scores were negative 0.5 and 1.5. And we have a mean of 0, standard deviation of 1. This is the default setting in StatCrunch. So if I open up a new tab, new window of it, stats, calculators, normal, look at that. It automatically defaults to a mean of 0 and a standard deviation of 1. If I do between and I say negative 0.5 and 1.5, the probability that negative 0.5 is less than or equal to x. In this case, x is z. I don't have a way of changing the letter in it. Is less than 1.5 is also 0.62465526. Notice that it matches up. The scores are the same. Converting to a z-score, we can do the same things and it still works out. Okay. So that's 7.2 right there. We're looking at 7.2 right now. 7.2 is the standard normal curve. So it has all the properties of the normal curve, all properties of a normal distribution. With two added requirements. Add in, rather than just being symmetric about the mean, it's symmetric about the mean equaling 0. And the standard deviation is 1. And the normal curve, we call them x values. We have the x values or x scores. When it's the standard normal curve, we actually say z scores, z values or z scores. By doing this, using z specifically for standard normal, this lets anyone know, or everyone know, that the mean is 0 and deviation is 1. When we say z-score. Okay. Now, in chapter 6 and chapter 7, we've used a lot of calculators. So at this point, after we've introduced several, here's a pro tip. When you open up a calculator in StatCrunch, verify the name in the upper corner, upper left. The normal, when you do it, stats calculators normal is going to say normal calculator. It also applies to the standard normal. If I'm doing a binomial calculator, it says binomial. If I'm doing a Poisson calculator, it says Poisson. So it can help you make sure you're not using the wrong calculator. If you accidentally misclick on something and have the wrong calculator, it can make this a challenge for you. Some other things you'll note, some common terminology. If you see something where there's like, you may see Z with a number down here as a number. For example, Z 1.5. What this means is, we are looking at Z values less than 1.5. I don't really know how much of a shortcut it is to write it that way. All we're saving is the less than symbol. But what it's doing is it's prompting you to find the area left of 1.5. That's calculator is normal. Like that. If they want, for areas to the right, it will say this. It will say Z with this funny symbol like that. It kind of looks like the infinity symbol. It's also the logo for fish frequently. That's alpha in Greek letters. So this is read as Z alpha. So if they ask you for the Z alpha score of Z alpha, where alpha equals 2.2, what they're really saying is Z is greater than 2.2, okay? And different problems will lead to different things. So let me just give you some practice stuff. I strongly encourage you to do these. If you can do all these and get the answers I'll put up afterwards, you've got this calculator down. So please find these values. If you have it, you'll be ready for a good portion of the midterm. Probability that Z is less than 2.15. Probability that 1.23 is less than Z is less than 2.15. I'm just going to throw up a bunch. Negative 2.97, we're going to do less than it. Let's do greater than negative 2.19. How about greater than 4.10? And let's do between negative 2 is less than Z is less than 2. Go through and use the standard on our calculator in StatCrunch. You might have to, you'll have to log into your homework and open up StatCrunch on the left. This is the homework tab. Oh, it expired. You can get into it in your homework class on the left on StatCrunch. On the left, it says StatCrunch. You click on it and it'll take you right to it. All right, pause this, work these out, and then we'll do them together. All right, I'm going to do the less than ones first. Let's start off with 2.15. Hit enter. And I get 0.9842 to 4 decimal places. To make it easier, I'm just going to do all the ones with the less than sign first. Let's go to negative 2.97. That's down a couple on the list. This one is 0.001489. And just showed them all. And that's the only ones that are less than. Let me do the greater than ones now. Right here, I've got greater than negative 2.19. Let's try that. And notice what it's doing is it's showing me negative 2.19 is right here, and it's shading the region that we're talking about. So if the wrong region is shaded, you entered it wrong. 9857, and we would round the 7 downward, down to a 7. Greater than 4.1, very low. Notice it doesn't even show any red because it's off the scale. The scale goes up to 3 and it stops. 0.00002066, really low. And then for the ones that have between two values, I need to switch to the between calculator. I'll do the 1.23 to 2.15 first. And I'm getting 0.09357,095. Wherever you rounded to, if you rounded to a different spot, fine. I didn't actually specify what I rounded it to or what I wanted when I asked you to do it. And we'll do negative 2 to 2, 0.9545. Now, according to this is the empirical rule, or this is 2 deviations away. Remember, the z-score is the deviation counter. 2 deviations away from the mean. That area is actually 95.45%. Not 95% like the empirical model. We use the empirical one because it's easier to remember for most things, and it's usually sufficient. Why do we use the empirical model or the empirical rule? So why is there a difference? The empirical rule doesn't match perfectly, but is close. But is close when z is an integer. Integers are like -3, -2, -1, 0, 1, 2, 3. No decimals. So when z or the deviations is an integer, you want to use the empirical rule. That's the one with all the percentages I told you to remember. If you're doing a problem on the test and that doesn't work, or you're doing a problem on the homework that doesn't work, then use the calculator, because they want the very specific value. In reality, in the real world, we use the empirical rule to do a lot of this. Where are examples of this in real life? Let's talk about some examples of this in reality. Let's say you're a manufacturer. You manufacture gadgets. And you know that defective items deviate a lot from the mean. And you don't want to sell defective items. So you decide to scrap the lowest 10% and the highest 10%. Find the z-scores that work. That will yield this. Okay. So we're going to assume it follows a normal distribution because we said z-score. Mean is 0. And like 10% over here, we want to get rid of this, scrap this. And 10% over here, we want to get rid of that. These are like the outliers. We don't want them. They make our product look bad. Which means the inner value is 80%. We have two options. If we're using the standard option in StatCrunch, I can say I want the probability that X is less than, and I'm going to leave this blank, and I can say 0.1. Or that's greater than 0.1. And then we can do less than 0.1. So, option A, probability that X is greater than, leave blank here. And then we're going to put in 0.1 over here. Compute gives 1.28155 or 16. And then I can also do probability that X is less than or equal to blank equals 0.1. And notice it says negative 1.28. Option B, do the between tab. Probability of blank less than or equal to X, less than or equal to blank equals the value we want in the middle is the 80%, 0.8. And it gives you my negative 1.2816 and 1.2816 here. Okay. Let's use a few more examples. Let's talk about percentiles and the GRE. We talked about percentiles before, back in the box plot and quartile section. Percentiles, and in particular, like GRE scores. They report your percentile score when you take the test. So let's say, example, you're in the 87th percentile. '87th percentile. This translates to, what this means in reality is 87% of the population scored lower than you. On that test. They are on the, like the GREs and SATs is always specifically that test, because each test is different, and so they only compare people taking the same test to that. Which is effectively in z-score format, probability that z is less than or equal to blank equals 0.87, click compute. Go back to standard here. I'll blank that out and I'll say 0.87. And at 1 percentile, it should be the left. The only problem with it, this and StatCrunch, is it doesn't say the letter Z when it's mean of 0 and standard deviation of 1. You just have to remember that. And compute tells us that the Z-score 1.1 M021-63911. And if a problem is not normal, is not standard normal, not standard normally distributed, we have a couple options. We can A, convert to z-scores and use the default calculator. Or B, I think B is easier. Update the mean and standard deviation in StatCrunch on the normal calculator. Okay. So they might give you something like this. A steel rod producer. Steel rod company produces steel rods that are normally distributed with a mean length of 100 centimeters. And if you know centimeters and meters, you would go, why not just say 1 meter? Because the standard deviation is in terms of centimeters. And standard deviation of 0.45 centimeters. I'm going to give you 2 questions. A, find the probability that a randomly selected rod is less than 99.2 centimeters in length. And is this unusual? And I'm going to change the wording up for part B. What proportion of rods are between 99.8 centimeters and 100.3 centimeters? Okay. Because remember, area can be probability of a randomly selected rod or proportion of overall rods. So part A, well, in both cases, we need to enter in our mean length. We can't put in centimeters, so we just have to remember the results are in centimeters. Mean is in 100 centimeters. Standard deviation is 0.45 centimeters. And I want the probability that a randomly selected rod is less than 99.2. Notice how once you put in a mean and standard deviation, it actually adds in the 68, 95, and 99.7 buttons. I'm going to open up a new one, illustrate it real quick. That's calculators, normal. The default calculator does not come with the 68, 95, 99.7. because it is just known that it's going to be 0, 1, 2, and 3. That's how the deviations work. As soon as you switch to a different mean or standard deviation, they throw that option in, and I think it's worth clicking on so that you get a better feel of what's going on. Those give us our deviation markers. So we want less than, we have probability that X is less than or equal to 99.2, and it spits out 0.0377, the 4 decimal places. If I want to do between, if I want to find the proportion of rods between, I'll click on between, and I got to update my scores, 99.8 to 100.3. Click compute. That 99.8 is less than or equal to X is less than or equal to 100.3 is 0.4191, the 4 decimal places. I can add in another one. Let's just throw it in there for you. What lengths represent the middle 90%? Well, now I don't know what those scores are, but I want this area underneath it to be 0.9. When I type in this box, notice it tells me a probability it's got to be a number between 0 and 1. If I put a number that's outside that region, it's going to say error. As soon as I type in a number over here rather than over here, it blanks out these ones. That's pretty handy. And then it gives me the values. So less than or equal to X, less than or equal to blank, equals 0.9. And it tells me 99.26 to 100.74. I didn't answer if this was unusual in part A. Is this unusual? Is it? This is unusual because the probability that X is less than 99.2 is less than 0.05. Less than or equal to 0.05. If the score is less than 5% of the time, it's unusual. I'm going to do one more example, and the reason why is because sometimes these questions are tricky. So let's talk about pregnancy in humans, the gestation period for human pregnancy. Human pregnancy. How long is a baby in the womb? It has a mean of 266 days and a deviation of 16 days. This is approximately 9 months, give or take 2 weeks for one deviation. So first question, what percent are more than 270 days? Which is effectively 9 months. The average month is 30 days. It's a little over 30. Well, let's update our mean. Let's update our deviation. I want more than 270, which means I got to click back on that one. I'm going to say more than 270. probability that x is greater than or equal to 270 is 0.40129 or 4013. I asked for percent though, so the specific answer needs to be in percentages. 40.13%. Homework will throw you off like that. A very preterm baby, like not just a little early, but very early, is born in less than 224 days. Which is about 7.5 months. Is this unusual? So let's check it out. We have our mean and standard deviation. We want to look at less than 224. I'll update that in there. And I get probability that x is less than or equal to 224, 0.0043325. This is less than 0.05. Actually, it's quite a bit less. So the answer is yes, it's unusual. They didn't actually ask for the score. They just asked if this is unusual. And finally, this question is the tricky one. What gestation period range rounded to the nearest day captures the inner 90%? All right. Well, the mean and standard deviation are staying the same. We're going to click on the between calculator, and I want to be between, I want the inner value to be 90%, so I'll say 0.9. And I get, when I fill it in, probability of blank less than or equal to x less than or equal to blank equals 0.9. When I fill it in, it says to one decimal place, 239.7 and 292.3. They want me to round to the nearest day though, okay? Round to the nearest day. If I round up on that, it would be 240 less than or equal to x less than or equal to 292. Does that work? Let's check. (89.5%). I don't have 90%. So that's standard rounding. Standard rounding doesn't capture 90%. That is 0.895. It only is 89.5%. So what you're going to want to do, let's just picture this on a number line. 239.7, 292.3. This region right here, I didn't draw the bell curve because I didn't give myself a lot of room for it. This is 90%. what I want to do is to make sure I have it, I'm going to go outwards from it. So there's a whole number here, there's a whole number here, whole number here, and a whole number here. That's 239. That's 240. Over here, I got 292. And over here, I got 293. If I do the inner range, 240 to 292, that's actually what I had there. The 240 to 292 was doing this region. It didn't capture the whole region. So what you want to do is go for the round to the day that will include the whole region. Which means even if I have a little bit extra, I'll round to that day and I'll round outwards there. In this case, I'm rounding outward from the range. So I'm going to use 239 days to 293 days. If I look at that, now I have the 90%. It's a little higher than 90%. It's almost 91%. But if I went any other way, I didn't get 90%. I had less than it. So this is kind of what you have to do. Notice if I even just use the values I rounded to, even if they said 1 decimal place, 239.7 to 292.3, I still don't have 90%, do I? 0.8999899, wait, 2 nines, 0.899772215. It's still below 90. So if I go to this, the probability here, 239 is less than or equal to X, less than or equal to 293, gives me 0. What did I say it was? 9085 when we did it. It's a little more than the 90%, but it's at least the 90%. But it does have it. But it's the closest to it that has the inner 90%. Okay? That's it for chapter 7. It's much shorter. All right? This is pretty much what you need to know for the midterm. Chapter 4 shows up after the midterm. And then it's on doing linear regression, some modeling. After that, we dive straight into the heart and soul of statistics is afterwards. But for now, peace. Turn this off. See you, everybody.